I think if someone wants to take one important message from this talk would be understanding the difference between intelligence and achievement. The field is currently focused very heavily on the achievement and the numbers and accuracies instead of trying to understand what does an intelligent system mean, what does it mean for a system to understand, to reason, instead of tying it to a certain number for a certain benchmark.
Iman, I think you would agree that we need to have better abstract world models, right? We need to have better representations. How's that going to work?
To me, it looks nearly impossible to build an intelligent system that operates without an abstract model of the environment and the world and knowledge. But right now, there are many questions that need to be answered before that. One of the issues that I have with the literature right now, and also including me, is that we don't even have basic answers to these questions. So after AlphaZero came, what happened is that the chess event became more popular and the quality of chess improved. Not because people used chess engine and just memorized moves, it's because they tried to understand what AlphaZero is doing, other chess engines are doing. So grandmasters actually use these tools a lot, but they don't go and memorize the moves by chess engines. What they do is that they develop theory. So they work on novel openings, they work on novel moves at certain position, novel strategies. They learn from these tools, not in a way that just memorizing. They understand, they create a knowledge, new theory. In image and computer vision, we had these benchmarks like ImageNet and all those benchmarks, and we saturated them, and we thought, okay, the vision is solved. But now we see that self-driving car is not becoming a thing right now because it's very difficult. Like in real world, there isn't a specific frozen cut of reality that with fixed number of examples. You have to build an agent that understands and reasons. So that's why I think is important to focus on, not the exact number.
MLST is sponsored by 2 for AI Labs. Now they are the DeepSeek based in Switzerland. They have an amazing team. You've seen many of the folks on the team. They acquired Minds AI, of course. They did a lot of great work on ARC. They're now working on O1 style models and reasoning and thinking and test time computation. The reason you want to work for them is you get loads of autonomy, you get visibility, you can publish your research. And also they are hiring, as well as ML engineers, they're hiring a chief scientist. They really, really want to find the best possible person for this role. And they're prepared to pay top dollar as a joining bonus. So if you're interested in working for them as an ML engineer or their chief scientist, get in touch with Benjamin Cruzier, go to 2forlabs.ai and see what happens. You know, we all accept there are limitations in reasoning in LLM systems, and some people say, oh, it's just because there's a missing feature, a missing tweak. We just need to tweak the transformers architecture and then they can do copying and counting and reasoning, all those stuff. Other people say all we need to do is let them access tools, right? So for example, like I want to have a system that plays chess. It can just use a chess computer. What could possibly go wrong with that?
So yeah, that's one of the most common arguments I hear and debate with many friends and colleagues and people, even at NeurIPS. And I don't personally have any issues with using tools. Humans also use tools. Everyone uses tools. So, but going back to our previous part of discussion, it's not about solving a task. It's not about achieving certain accuracy on a task. Then it's about understanding. It's about creating novel knowledge, creating novel goals, achieving those goals. So there are two arguments I have against the tool use. So one is that, first of all, it's not just one tool, right? So there are like for chess, yeah, if your only goal in the world is to do well on chess and beat some humans, yes, you can look at, I don't know, a chess engine as a tool and just give moves to it and get moves and play chess and win. So it won't be just one tool for your whole life. It will be many tools, right? So if you look at some reasoning tasks, right, like solving a math, logical problem, planning, so it involves many steps, many states that you need to navigate and learn. And even with tools, you won't be able to use, you won't necessarily will use only one tool. You will need many tools. So it will be like, I don't know, at some point you will need to use 5 tools, 10 tools. And then the tools may become complicated. They might not necessarily be like, you give input and you get output. It will be complex. So essentially, it will reduce to the same problem, right? What if I need to plan for 10 different actions? If you look, and so at that point, you still face the same problem, right? So that's one argument. And for the chess, also there is this argument that if you use tool, it's fine to use tool, definitely, but you don't necessarily be able to know if the system that uses external tool understands that task. So looking at the chess engine, you could use a chess engine and play and win, but you won't necessarily understand why did you make those moves, why there is this move in that position, what constitutes a good position, bad position planning. So actually, because I'm a huge fan of chess, I watch chess competitions, and so I follow what's going on in the chess world. What happened is that after AlphaZero came, so humans, instead of like everyone thought like the chess as a sport and a competition will be kind of will lose its importance because there is this system that wins any grandmaster in the world. But what happened is that the chess event became more popular, and the quality of chess improved. Not because people used chess engine and just memorized moves, is because they try to understand what AlphaZero is doing, other chess engines are doing. So actually, they wrote a book on understanding the moves of AlphaZero, right? So the famously AlphaZero has this moves that sometimes it tries to push from the left or right corner, and these moves have not been like seen before, right? But you could say that I don't care, this is a move that goes like gives me advantage and wins. Or you could understand why this moves, this kind of moves improve chess, right? So grandmasters actually use these tools a lot, right? But they don't go and memorize the moves by chess engines. What they do is that they develop theory. So they work on novel openings, they work on novel moves at certain position, novel strategies. They learn from these tools, but not in a way that just memorizing. They understand. They create a knowledge, new theory. And I think this distinction of like how humans use chess engine versus how people think we should use chess engine is very important. So if someone claims that chess engine, like you can use chess engine for your LLM as an external tool, I'm fine with that if you want to develop that system. But my metric for measuring how good that system is that if you let that system or LLM or any system use that chess engine, after a while it comes up with a theory. So one example would be that like in chess, there is this principle that in the opening phase you should have a control on the center, because you have control over more squares. It allows you to uh, uh, like in the next moves, it allows you to have more squares, and it prevents your opponent to develop its pieces, right? So development of pieces, controlling the center are the principle of the chess. So if you start with any system and a chess engine, and after a while it comes up with why it is important to control the center, because the openings, like you could train a model on all the games and it will learn as a distribution and statistics that the first moves are for white e4, d4, or c4, right? Like the first the center pawns. So the reason behind that is that they want to control center, right? Yep. If it comes with that new knowledge that understands why it matters using a tool, it's fine. But if it's just, using a chess engine and gives moves and back and doesn't have any understanding on what's going on, then all you did is that you got like high rating on chess without really knowing what's going on.
How puritanical should we be here? So, LLMs, they act as if they are doing reasoning in many, many circumstances, but they're prompt dependent. You give them the wrong prompt, you put distractors in there, it brutalizes it, it doesn't work. So how do we interpret that? Do we say it's not reasoning because of the brittleness?
The short answer is yes. So the way I look at the prompting and the reason I also don't necessarily think that like exploring different prompting helps in terms of really understanding, like improving the systems, is that I look at the prompting is that I look at LLMs as learning as a system that knows a lot of distributions, right? And then the prompting to me looks like conditioning those distribution, nudging those distribution to like maybe specifically steer the model towards some direction. And so you could use prompt to do anything you want almost, but that doesn't mean that the system is understanding what's going on behind the knowledge. So my problem with the classical way of the way we train the system is that we look at everything as a distribution, and when you learn a distribution by construction, our loss function is that you learn a distribution that minimize the distance between your distribution and the some distribution that you infer from data, right? And once you learn that distribution, that's all the model cares. So once you learn that distribution, you just stay in that distribution. And that the problem is, there are many problems with that. The first one is that by definition, by construction, these systems won't be able to understand what is beyond that distribution, right? By construction, we train the models to minimize the loss and stay like within a boundary of a distribution. And that's what leads to all the problems, right? You change something, system breaks. You want to measure like how the models perform on like different distributions, they can't do that. And like all these problems, because that's how we trained our models. How do you expect the model to stay in a box and then like you ask it like what happens outside the box, and like you constructed that system this way. So I think that's one of the issues. And another issue with the way we train, I think, our models, I don't have, by the way, answers to how to fix this right now, but another issue is that when the way we train with, for example, cross entropy loss, right? So let's say you are like, you are teaching models to do arithmetics, right? What we do is like 2 plus 2 equals, there are like, assuming there are like 2 is a token, plus is a token. So these are the tokens. And then in the text, there is 4, right? So all the model has to do is learn after 2 plus 2 equal, it should output 4 and some context maybe. So it doesn't matter for the system that this 4 comes from understanding the whole natural numbers, the line of numbers, addition, can we do this or not, or it's just memorization or maybe some other thing, right? So there is nothing in our loss function saying like it's important that you understand numbers and natural numbers as a concept, which later will be grown to, I don't know, rational numbers or like real numbers and all these concepts. All you have to do, all I care is that after 2 plus 2, you should give me 4, right? And because of that, we don't know if the model can come up with that understanding and building a world model or kind of concepts of what's going on. But yeah, I think these are the main issues with the like all those. These are the consequences of, I would say, all the things we are doing to train the systems.
So you said to me that you're overwhelmed by the lack of progress in, the sphere of intelligence in AI research at the moment. Tell me more.
Oh, okay. Yeah, I mean, there's like there are two sides to this story. One is that um, obviously I think we are living in a very important time and very exciting moment, and there are lots of progress being made. Lots of people are investing in AI right now. There's lots of research being done. So from that side, it's very exciting. On the other hand, I think like in my opinion, the way we are doing research in the field is not necessarily optimal, and the way we designed our uh, metrics and the way the system works in general is not necessarily optimal. So, for example, right now the current way of doing research, most of the uh, research is that people believe that research is always an incremental process, and I don't disagree with that. You will always build on top of work of other people, um, but my issue with how the research is being conducted right now is that we don't by reading new papers and learning all the new papers, we still, compared to, I don't know, 2 years ago, 3 years ago, 4 years ago, we still don't have a better understanding of how these systems work, right? We do not know that, like, whether we are moving towards the right direction or not. For example, like most of the papers these days have a hypothesis is that, like, if you do this, and then this will happen, and then they run experiments show that, like, yeah, if you do this, then this happens. Then there will be another paper saying that if you do this, then this happens. And then there will be other papers saying that all these papers had this assumption, and then if you have a different assumption, this will happen. And then still, after like reading, I don't know, 10, 20 papers, you still don't have a coherent picture of like how these systems work, like what is the general hypothesis. So I think what uh what is, I think, good about many other fields like physics is that you have a hypothesis saying like, this is my model of I don't know, a transformer, right? This is how I think a transformer works. And then after that you say, okay, if my hypothesis is true, then there will be these consequences, right? And then I'm gonna do a design an experiment and measure that. But this is now not how things work. The way people approach this problem is that they look for solutions without before understanding the problem. So I think that's one of the issues that I hope, like, at least people spend more time on, like, understanding things rather than focusing on the solution and what we can do. I am always like uh, I think it's more important to understand what is happening right now. What are the problems? What are the uh, pros and cons of these systems? How do these systems work, right? And then once you have a like at least hypothesis or mental model, or like how these systems work, then you can build on top of that. But otherwise you will maybe run into like papers or like research that think like, instead of trying to understand how, like, prompting, like, you could say my model of prompting is that it will nudge the distributions, it preconditions the model, and then if there are a few distribution and the model is interpolating on that, then this will happen, right? And then you could run a few, like, test this hypothesis. But like what happens is that someone explores that what happens if you tip a language model, and even if it like increase your accuracy by 5%, you still don't know what's going on, right? Like, you, after reading that work that increased the performance of the model like a few percentage, like all those work, you still don't have a better understanding of the uh, models, and then that will be makes it very difficult to improve those systems, right? And then there are other, I think, aspects like I think, like, from the theory perspective, I'm not an expert in theory at all, but I think maybe our theory is also too rigorous, I think, for the moment, because the problem is so hard, and the current theory lags far behind the state of the practitioner. And then they want to stay rigorous, very rigorous, and like develop it, but it's very hard if the theory is, doesn't like become more relaxed, so it can at least be like have a faster progress. So I think those are the main issues. And then from the other aspects, I think like it's given the amount of interest and investment and in the AI literature, then there are many people working on the field, which is really, really great. But there will be other challenges, like the reviewing process, the peer reviewing process is really difficult and noisy. I don't have a unfortunately solution for that to propose here, but I think we can at least think about these problems. How can we improve those processes? And yeah, I think these are the main I think challenges of the AI literature and the AI research community right now in terms of research and how the research is being conducted.
How can we bridge symbolic AI and connectionism?
Yeah, that's a. I think. I mean, there are a couple of ways to think about it. Like, I think you could have a symbolic model. I'm not right now. I'm not saying that like this model, like symbolic model versus non-symbolic models or deep learning is good, bad, or like think work. I'm thinking about more like fundamental ways of like, given any systems, is there a way to understand if this system is understanding a concept, is able to reason? But in general, I think it is fine to start and like integrate these two as a, like, maybe we start with a separate module, and then maybe eventually, like by marrying these two fields, like it will become more integrated and improve over time. But it's very important to like not look at these things as two separate systems. Otherwise, it will lead to problems of using an external tool and all those things. So there should be some notions of understanding and like the model itself should be able to have a word model, should be able to understand if I need to update this or not. So one other thought experiments that I have is that, like, imagine right now that we are talking, I tell you the area of a square is PR to the half, like the power of half, I don't know, something like that. Pi times 2r, right? So you wouldn't accept my argument, right? Like you could prove mathematically that this is not correct. But if I tell this the area of square is pi r to the power of 3 to an LLM, because there is no module in the model system that's saying like, is this making sense? What do I think about the area of this circle? It should ideally won't be, it shouldn't accept it, but we don't have that system. So I think that's one of the things that I think one of the examples of why we need another component, why we are missing at least one component that after a while learns comes up with its own belief system and like knowledge representation. And when something comes, it may update its belief system or may disagree. I wouldn't agree that, I don't know, the area of circle is something else, because I can't prove it to you right now. That's it. If you have another proof, I will read it, but I will doubt that that proof is correct, right? So that's very important. But there are other belief systems that I'm open to change. Like the best place to eat in Vancouver, I'm open to change and try your suggestions. So I think it's important that the systems should to not be separated and like be looked at as two separate components. It should be a like integrated loop.
Yeah, and I think it is interesting that you say that humans don't always reason, but we're capable of doing some privileged form of cognition that we might call reasoning. And also, you could argue that the LLMs have a spectrum of modes. So sometimes they're doing surface statistics, and maybe in certain circumstances they're doing at least some approximate version of reasoning. So there seems to be a spectrum. Tell me about that.
It's I think if you look back, obviously we can admit that kind of what these systems today are capable of kind of surprised the field and everyone, I think. But I think we kind of sometimes get read too much into it and what these systems are capable of doing, and the fact that like the some claims say that the models can reason and like there's a spectrum. I'm not sure about that actually, that these models can system. What they are good at, I think, is doing some sort of interpolation. So it's not that they're just memorizing things, they can't do anything beyond training data. They learn many things from different places and they learn different distributions, and they do interpolate between these things that they've learned. So I think that's what gives, I think, the illusion of what these systems are capable of reasoning. And if the domain is very limited and closed, for example, a specific domain where the overall space is closed, the interpolation of the model seems enough to assume that these models are capable of performing in that domain. But I think in general, there is a very huge distinction between the achievement and capability of a system and the intelligence and other like intrinsic capabilities of the system. So these two are different. But currently what we do is that we mix those two together. So for us, right now, it's like if a model performs good at a coding benchmark, it means that it has reasoning. If it does good on math benchmark, it means it's doing like some sort of reasoning. And when we mix this together, it makes argument and like understanding these systems very difficult. So I think it's important to discuss the distinction between intelligence and achievement. So intelligence by default, it means like by definition, it means about the capability of system, not and how it can grow and at some point eventually becomes capable, not necessarily what it is, how capable it is right now, right? So achievement is about measuring what the system is doing on a specific domain or task or benchmark. So these two are different. So if a system is intelligent, eventually it will be able to do well on some sort of benchmark, and but necessarily the other way around is not correct. So if the model is doing well on a benchmark, it doesn't mean necessarily it is intelligent. But because it is hard to measure, right, to the intelligence in general, this is an open question. We set a benchmark and say an intelligent system should do good on this benchmark. And then when a model or system gets good, we say this is doing reasoning. So these are different. I think intelligence is about how a system in a long run is able to perform well. So there was a good, very interesting picture in Ilya's talk at NeurIPS this year, and in that figure showed like there was a regression line between the body mass and brain mass, and that figure showed like how the different species scale in that sense. So my take from that picture was that intelligence is not about where you are in that scale right now. It's about how, like, the slope of that figure. So if you are thinking about the scaling laws, intelligence is the slope of scaling, not what point you are at.
Yes, I love all of this. I mean, you probably know I'm a huge fan of Francois Chollet, and he's always at pains to say that intelligence is not skill. it's adaptation to novelty, it's skill acquisition efficiency. So there's something about the macro adaptability which is important. And actually, when we were discussing this before, you came up with your own test for intelligence, which I'm going to call the Iman Moon test, which is, basically, imagine we start from cavemen and we land on the moon, and sort of how quickly can we do that?
Yes. So yeah, that came from a thought hypothesis, right? So just to again reiterate the distinction between intelligence and achievement, right? So imagine a caveman. So if you go back in time and give MMLU or GSM-8K to a caveman, I would argue that the performance would be near zero. And current models get near like 80%, 90% accuracy on these benchmarks, right? And do we really believe the current systems that we have are more intelligent than a caveman? So intelligence is about the system that a human possesses, not how well it's doing on a benchmark, right? Even if you go even further, like some great figures in history and science, like Aristotle, right? If you give MLU to Aristotle, I don't think it will perform nearly as well as current LLMs. But do we really believe those LLMs that we have are more intelligent? Because intelligence is not about how much you achieve on a certain task. It's about how well that system, that human, can, if it spends time, learn something and grow.
So how could we measure this? Because, like Chollet had this formalism for measuring intelligence, but it wasn't computable. And benchmarks, they just get saturated, they get good-hearted. How can we build a new suite of benchmarks?
Yeah, that's I think I don't have a concrete answer to that. I'm thinking about it a lot, but I don't think right now I do have an answer to that. But we can maybe not. We can at first start with something that is not necessarily objective, but maybe we can start by asking what kind of system do we want? What does intelligence mean to us? What does achievement mean to us? And then if we maybe start with a kind of axiomatic definition and characteristics, then we can, at first it won't be objective, and I know it will be not concrete and open-ended, but if we start thinking about these important problems, we may come up with some way of measuring it. So it is in general, measuring intelligence is very difficult. It's even for humans, it's not trivial to measure intelligence of humans. But I think we can have define some desired properties that we want from a system. So those desired properties might mean something like the system being able to perform well on novel tasks. And then definition of novel itself is not easy, but I think we can start from some here and then build on top of that and think more on that. So because there was a nice paper by Gilles Guignac et al. And it's called on definition of intelligence. I think that was a really good read. It's not in like circulated very well in the machine learning community because they have background in psychology and cognitive science, but it's really nice paper. It defines very formally what is the definition of intelligence, what is the definition of artificial intelligence, what are kind of forms of intelligence we are looking for, and we can start from there and think more on those problems, and maybe we come up with something better. So yeah, that's what I'm thinking on these ways. But in general, I think the direction should be towards measuring novel tasks. So for example, if you're training a model to do coding, at least what you could do is that for me, a better measure would be how fast that system can learn a new programming language from scratch, right? So a system like an LLM could do very well on Python or all the languages it's been trained on. If I create a new programming language and ask it to write a new language, new program in that language, how fast it can learn that language and how good it can write programs in that language compared to a human that never seen a language before. Because I think one other things that we can do is that compare the how humans learn and reason, and compare it and contrast it with how these machines are learning and reasoning. So yeah, I think we can think towards that direction, but I don't have a concrete.
Yeah, it's very slippery. There's a great paper by Pei Wang on defining intelligence, and he said that it's very anthropocentric, and in different fields people use different techniques. So we could have basically a copy of a human brain, and that's the most anthropocentric. That's not particularly useful, is it? Or we could have notions of behavior or more abstract capabilities, so being able to write Python programs, or functions, so having things that do planning and reasoning and all these abstract cognitive functions, or maybe even having things that have certain principles like emergence or certain characteristics or something like that. Very, very slippery. But just before we move off that, you cited this paper from Psychology. I'm very interested to know what their definition was. For Pei, his definition is very much about adaptivity. That seems to be one of the core things for him.
So yeah, actually, that paper discusses lots of other works on studying and understanding and defining intelligence. I highly recommend that paper. So yeah, the focus of that paper, the main emphasis is on novelty. So the definition of intelligence in that paper is that the maximum capability and capacity of a system to achieve a novel goal given some time. Like obviously, you can define many different programs and systems that, given infinite time, eventually they could reach to a goal. But the time is also important. That's why I also mentioned the slope of scaling and why it matters.
Do you think agency and autonomy comes into intelligence? So, basically the ability to set your own goals, or do you think we should think of intelligence purely in the frame of this is a thing, it has a goal, and can it achieve it?
No, I think actually agency and the system as having some concept of what it wants is very important. So I was reading a book recently. It's called How We Learn. Why Humans Learn Better Than Machines for Now by Stanley Duan. And in that book, he discusses lots of great topics and how humans learn, how machines learn. And it comes from neuroscience background. So lots of new insights, at least for me. And one of the things that seemed really interesting to me was that that one of the pillars of learning for humans is active engagement. And essentially some humans have very it's very hard for humans to just observe and don't get involved and just watch something to learn, compared to having them set their own goals, being able to actively engage in the environment, explore, maybe later exploit, and all these things. So without that, that's actually, according to that book, is one of the necessary conditions. Yeah, it's not something that is good to have; it's something that you must have. So I think that's one of the important topics, and I think for me the implication was that if you want to build a really intelligent system, supervised learning won't be enough. So you need an agent to ask for what should I do next, and be able to ask questions. It's not like you just observe and see, okay, I learned this, I learned that. It should be something like, now I learned this, what do I want to learn? Maybe I haven't understood this well enough. I need to explore more. And
let's explore this. This is fascinating. So controlling the center is an abstract category, right? It's an analogy. And Douglas Hofstadter said that a concept is a bag of analogies, essentially. So there's moving to the center is something that we all understand at some abstract level, but what does that actually mean? I think many concepts in chess are quite fuzzy, right? So what that actually means in many, many different situations is slightly different. So the question is, what's the difference between AlphaZero? It discovered this move 37, and if you play it millions of times, this move 37 in its behavior space emerges as a mode. So you could argue that it is doing reasoning, but it's doing an emergentist form of reasoning. So rather than having some notion of in the center, its behavioral profile acts as if it has a notion of in the center. And how is that so different from the way our brains work?
Yeah, I think so again, like that if so that there's this thing like AlphaZero, AlphaGo, and all these systems are able to understand the environment they're put in, right? So they like they explore the environment, they play a lot, and they are able to eventually explore all the like most of the kind of positions in the Go or chess or many of them. So uh, eventually they will be able to take rational decisions because they understand the value of each state and do that. But that doesn't mean they come up with this concept. So for a chess engine, it is that this move improves the value of this position, right? But it doesn't necessarily transfers to other aspects of life, right? So in chess, for example, you could argue that controlling center means controlling important or strategic positions, right? You could once you learn this, you could also apply it to other aspects, right? This is not just about 4 or 5 squares in the center of a chessboard. It's about importance of a specific positions in different parts. So it could be about controlling an important a road in a country, controlling an important passage. So that form of abstractions is, I think, and the way we store knowledge and learn is what allows us to scale very fast. Once we learn this in chess, we are able to scale it, like use it in across other domains. But systems like AlphaGo or AlphaZero are not able to do that because the word to them is just that, and they don't have this kind of abstract representations and knowledge. So I think I'm not saying that learning abstractions is necessarily the only way that you could build an intelligent system, but certainly it's helping humans to scale way faster and improve faster than machines.
On the matter of generalizing out of distribution, so what we're starting to see is, I mean, obviously chain of thought is used a lot, which means that you can take something which is trained on a distribution and you can kind of like manipulate. I suppose you're doing some kind of directed retrieval to create, you know, compositions in some fixed way. So there's chain of thought prompting. Some people are doing program induction. And it certainly seems to be the case that with a few examples, maybe with chain of thought, you can get a language model to induce a very rich and diverse set of programs. And many of those programs seemed to have some kind of abstraction. Another thing we're seeing is transduction, which is where you do some kind of active fine-tuning. So you take the test instances and then you kind of like modify the existing model a little bit so that you get generalization in this domain. So there's loads and loads of approaches that seem to be working quite well for making these things do better OOD. What do you think about that?
Yeah, okay. So yes, so you could do like there are lots of ways to explore this, right? Like chain of thought, program synthesis, all these topics. So my question, which I'm trying to think about like these days a lot about, is that all these systems, all these methods, all these directions are built on some assumptions, and the assumption is that there is something going on in the model, some kind of understanding that we need to improve that, right? I'm not quite sure if right now there is that if that assumption is correct, right? So I'm not saying that it's correct or incorrect. I'm not sure about it. So if that assumption is incorrect, then all the things you are doing, chain of thought, all the other methods for improving this kind of reasoning uh, may not be helpful, right? So I'm like, what I'm thinking about like is that like taking a step back and really asking this question, like, is there anything there like beyond some interpolation between distributions, right? If there is, then sure, we can continue and build up on top of that. If there's not, then what are we doing? Why are we trying to do all these like methods that it's very difficult, by the way, because we are also doing it in a like kind of ad hoc way. There is no cohere model of what the transformer model is doing at scale. So it's very, very tricky, I think. So right now, I'm leaning towards that the models don't have a correct representation, and the way we build these models by construction is limiting. So I don't really see how other like extending this would be helpful. Like there was an old example of like uh, if you want to land on moon, you can do it with an airplane, right? So there are two questions. If you have an airplane and you want to land on moon, then you could improve like the speed of plane. You could make it lighter. You could like make it go faster or all these things. But it doesn't necessarily help you land on the moon. So you could also work on like how would like wings should look like. How would like the what kind of uh, runway should we use to have a faster takeoff? All those things. But that doesn't necessarily help you with your goal, right? So I'm saying like I'm not saying that it is impossible like right now. I'm saying that like we should ask a question: is this the right vessel? Is it like does it make sense? So yeah, in general, it's I think we should take a step back and think harder on the problem.
Onto scaling laws. So, Noam Brown is talking about this new test time scaling law. You've said that it's very, very difficult to convince people that scaling laws, don't work, because you'll always have a group of people that say, oh, just over the next hill, just, if we 10x the parameters, 10x the compute, then we'll finally get there. How do you convince people that they're wrong?
Oh, yeah. I mean, I can't really convince because the issue with the scaling law is that if I spend millions or billions of dollars and train a model like I don't know 10 trillion parameters on 100 trillion tokens and come and show you, hey, this is the model, and it can do even simple mathematics beyond what it's been trained on, right? It can create new knowledge. And then someone can claim that, hey, this is not the right scale. Like if you scale it to 50 trillion parameters, there will something emerge. And then because my argument is not theoretical, I can say, no, you're wrong. And because I won't be able to train that model at 50 trillion and spend a few $billion, I can say you're wrong. So there will be always this debate that something will emerge. And by the way, I don't have issue with scaling, right? Like scaling as in a sense that like I'm not saying that it will hurt or it won't be helpful at all. I'm saying like if you are thinking about the scaling, that that you should focus on the slope of your scaling. You shouldn't care about where you are right now, right? So if you want to compare two different systems or like one architecture with another, you shouldn't care about like one what happens at the 100 trillion or will something emerge. You should say, look how fast these models will be able to learn and do novel things. So right now, I think in that sense, the slope is near zero for all the architectures and methods we have, but we can focus on the slope rather than the points and endpoints.
On the slope then, how does the slope of human scaling compare to LLM scaling?
Uh, yeah, that's one of the interesting things. Like, weren't able to do that, but it would be interesting to. I think there are many studies. I'm not an expert in the field, but there are many studies showing that how humans versus models react to novel environments, right? If we compare those, I don't have any number, but I think there are many studies showing that humans can adapt to new environment. They can learn new environment very easily, much easier than at least LLMs. So I think the slope of human is faster, better than the slope of LLMs. But it could be that there will be a better species with better scaling, better slope, and I look forward to it.
Very cool. So, Iman, I think you would agree that we need to have better abstract world models, right? We need to have better representations. How's that going to work?
So I think, yeah, I mean, to me it looks nearly impossible to build an intelligent system that operates without an abstract model of the environment and the world and knowledge, right? But right now there are many questions that needs to be answered before that, and we don't even have like that. One of the issues that I have with the literature right now, and also including me, is that we don't even have basic answers to these questions. So imagine you want to learn a function, right? So one way to represent that function is representing with table, right? Like input x and output is y, right? And then imagine there is another way of representing the function, is representing it in a way like this is a polynomial, right? Like y equals x squared plus some number, something like that, right? And we don't know, like right now there is no objective measure, and we don't even have an answer to that, which one is better, right? You might come and say like the second one, where it has a form, it is like it's abstract or like something like that. This one is better, but we don't know like why would someone claim this one is better than the other, right? I also believe the second one is better, but we don't have we couldn't quantify this, right? The second one is certainly not like someone can claim that the second one is compressed in a compressed form. You don't need a table, you just need a polynomial. But I don't think that's that's necessarily correct, because in order to represent something with polynomial, it's not about the number of characters in a string. It's about concepts, right? So in order to define a polynomial, you need to understand what does a function mean. What does function x squared mean, x to the power of n? And then that requires understanding what does continuity mean, what does a real number mean, like all these concepts. So if you want to encode everything that it takes to reach to y equals x squared plus some number, then that maybe even is being larger than the table, right? And then if your only goal again is achieving something, referring back to our previous discussion, then these two are equal, right? You give input and both of them give you output, and that one is even faster. You just have a lookup. So we don't have a way of comparing two representations. So if I want to sum up, is that in order to answer all the questions you ask, we need to start with understanding how to compare two representations. Once we do have, then if you have a good measure of comparing two representations, then we can build on top of that. But we don't currently have that. Actually, I was talking to a friend, like, how do we compare these two representations? And I said, like, I don't have a measure, but similar to the idea of like at some point in time, someone came up with the idea of like formalizing the concept of generalization. Before, like 200 years ago, like generalization wasn't a concept in a sense. It was a word, but so it says like one representation could be more beautiful than the other, right? Like a polynomial is more beautiful than a table, but we don't have any formal way of defining what constitutes something being more beautiful. But we are thinking on about these problems all the time. So
I guess the core here is whether deep in your bones you are a connectionist and you believe that it's possible in principle for this kind of thing to work. Because obviously, when we'll talk about your paper in a minute, you've designed a symbolic test to prove that certain types of reasoning can't happen or don't happen in an LLM. In 1988, there was this famous connectionism critique by Fodor and Polishin, and they argued that these systems don't have systematicity, they don't have compositional generalization, they don't have invertibility, so they can't, explain why they did things, they can't canalize their knowledge in the way that you're talking about. But other folks like Smolensky, get his name right, in 1990, and certainly people like Bengio, they argue that, it's not a problem. All of this symbol use can just emerge, at some level of complexity or whatever. So do you think that in the future we can make LLMs do this kind of symbolic reasoning?
I think when we are talking about symbols, like the notion of symbol is not like we have to define the notion of symbol. Like, is symbol something concrete and predefined, or something like? Do you agree that maybe do you accept the middle activation of a model, a deep learning model can represent a symbol or not? So if you agree on that, that could be looked at as a form of symbol, then I think yes, the model will be able to do that. Otherwise, if you think that symbolic is like the form of like separate external system, then no. I think I'm more leaning towards like symbols being emerged as a part of computation inside and.
Oh, that's very interesting. Yeah, because I suppose that there's a spectrum of views. I mean, that there are some people who think that just pure connectionism symbol use can emerge. There are people who are quite sort of like in the middle. I think I'm in that camp, which is that we can build LLM systems. So maybe sort of agent LLMs that talk with each other, or maybe neurosymbolic architectures where the LLMs can use tools, or some combination of the above. But you're in the camp that we could, in principle, just have a pure play neural network and it could do, symbol use.
Yeah, I mean, right now I don't have like any I don't see it, like in theory at least, right? Like I don't see in theory why such a system won't be able to create that kind of symbols theoretically, but like it could at some point create symbols and do computations on those symbols. I'm not saying like this is the only way. We shouldn't have anything, like not very experienced in that sense, but I don't have this kind of thing. The same goes with like other like when I discuss like architectures, right? So I don't know if the like maybe transformer is the right architecture or not. But right now, in theory, at least given the context and assuming the model is generating tokens because it becomes Turing complete, I don't have any reason in theory to believe that's a limitation right now. It could be that other architectures are better, like we can develop better architectures. It's just that right now, I don't see that as a limitation.
Okay, but you do think we need to have Turing completeness for symbol use, so we could somehow come up with a neural network which is Turing complete.
Yeah.
Okay. Yeah. We're not there yet, but maybe.
Yeah. I think like when we're defining intelligence, like at some point, like Turing like being able to do Turing complete is like operation is like a necessary condition even.
Yes, I completely agree with that. We should talk about your GSM-Symbolic paper. So this is a landmark paper. It did the rounds on socials. Millions of people in my community said that I had to interview you because it was amazing. Sketch it out for me.
Oh, okay. So a little bit of background. Like we were working on understanding reasoning, and we were exploring a few ideas about improving the reasoning of the models. In terms of like increasing the amount of computation a model does per output token. And for that, we needed to evaluate the model and also be able to have a robust evaluation, and then eventually have maybe better training data. So we started with the evaluation, like creating a small sample from GSM-Symbolic, just templates. And then just to do a sanity check, we ran the experiments and see just like how close these numbers are to GSM 8K, and we observed that there is a huge, for some models there is a very huge gap. For example, Phi2 had like 20% gap, 14% gap, something like that, and then there's also huge variation, right? So yeah, we like kind of got sidetracked and like explored this immediately to understand like what's going on, right? And one of the second, like after we had the initial GSM symbolic, the second thing I was working on was the GSM no-op version, where you try to trick the model essentially, and that you add one clause to the question where that clause carries no logical or like arithmetic operation. It's like if you completely ignore that clause, you will be fine, right? So that's why it's called GSM no op. And then that was the second one. In the paper, we have a different presentation, but like we explored this second, and then we observed a very huge performance drop. So then we came back and tried to understand like something in between. Like we try to uh, be more like try to create like easier benchmarks than GSM no op by just adding one clause that carries operation, and then adding two clauses that carries operation. So you can't ignore that and see how the models perform in that. And to like among all those benchmarks and experiments that we designed, the surprising thing to me at least is that the variance of the performance we observe across the model. So I wish we could at least do some sort of cross evaluation across students of how students would perform if you change like the words in the problem without changing the numbers, right? Like if you, instead of saying Amy has 3 apples, you can say John has 3 bananas, right? They're the same, like in terms of logical uh, reasoning. And I wish we could do that. And I think I hope someone also explore these things, like how would human student perform if you just change orange to banana, compared to an LLM. And so to me, the most fascinating part is the variation in the sense that why does this like gap exist even though you only change the number. So we have a benchmark called GSM names, where we only change the proper names of the question. We don't change the numbers or add anything to the question. So yeah.
The frontier model, I mean, to be honest, they still did quite well. I mean, I would expect them to just like drop off, because like Sabaro Kamahati has done some experiments with planning, and he did this mystery blocks world where he just changed the name of the symbols to like random things, and it dropped off a cliff. And the O1 model kind of like made it up to non-trivial performance again, but there was a huge decline. And I guess reading your paper, I was still somewhat intrigued that the frontier models, they did obviously like much worse, but it was still pretty like non-trivial performance.
There are two things. Like personally, I don't know. Like I think overall the GSM 8K should be very simple benchmark. Given we also, there is also this factor that we don't exactly know on what kind of data these models have been trained. It could be, I'm not saying it is, but it could be the case that these models are also being trained on some sort of synthetic data generated from uh, questions similar to math work problems like GSM 8K. And we also know that all the companies that are trying to build LLMs, they are also getting lots of human created question answers in math and other domains, right? So we don't exactly know, like that's one of the issues with not being like transparent about what kind of data at least the model's been trained on. But it could be the case that the frontier models have like access to better data quality and data format similar to GSM 8K. And it could be that they have unlocked some kind of emergent ability. But if that were true, then at least I'm not a believer in benchmarks, but there are again different benchmarks that are similar to GSM-8K, slightly more difficult. And in those benchmarks, I think someone tried a similar idea that we did on GSM-Symbolic on math dataset, Hendrix math, and then they observed a larger performance drop for frontier models as well. But overall, it's again for me, it's not about performance. It's not about, like, I prefer a model that if you make the question difficult, the performance drops 10%, but there is no variation, because if it understands the question, it understands the question, to a model that drops like 1%, but there's a like large variation. So it's, to me, it's not about the number of like the accuracy number. It's about why would a system that understands is able to do a set of logical steps tries to do different sets of logical steps and gets it wrong if you change orange to banana in a question, right? And that probably is coming from because we trained the system to learn a distribution. There is no concept of, in this question, it doesn't matter what kind of object that is. It's about the number of objects, right? So these two for us seems trivial, but for a system that is being trained to predict the exact object in the question during the training, it's non-trivial. So yeah, I think overall in all these systems, I don't think they truly understand this concept. Like you could change any, like, I wasn't like doing a search on those kind of things, but you could, like, if you spend enough time, any question that they get them wrong, I truly believe if you spend enough time, you could change that question to a form that the models, including frontier models, get them wrong. But unfortunately, the field looks at these things as an accuracy number, not necessarily what does it mean for a number to drop or what does it mean for a variation to increase. And they kind of, now I think the field is trying to move from GSM-8K because the performance is reaching like 95%, near 100%. And now I think, like yesterday in the workshop, there was like, oh, we have a new difficult benchmark called frontier math, and this has been designed so that like now frontier models get 10%. Now let's increase that 10 to 90. I like, my problem with benchmarks is that they're like a cut of reality, and once you freeze that, you could change the system in a way that indirectly you change the system, but it has a like impact on the performance. So eventually that benchmark will be always saturated, but it doesn't, at least to me, it doesn't matter. Like that system, unless we change something fundamental, that system may get 99% on that benchmark, won't be able to create new knowledge, won't be able to understand what's going on. And to me, that's what matters, right? So in image and computer vision, we had these benchmarks like ImageNet and all those benchmarks, and we saturated them, and we thought, okay, the vision is solved. But now we see that self-driving car is not becoming a thing right now because it's very difficult. Like in real world, there isn't a specific frozen cut of reality that with fixed number of example. Reality will change. You have to build an agent that understands and reasons. So that's why I think is important to focus on, not the exact number.
Yes, and benchmarking is a big problem. So as you say, I'm sure many of the frontier models have basically memorized GSM-8K, and certainly we should be moving towards more of a generative benchmark type thing where, you know, of course it's not deterministic, but we have some generative system and we sample from it enough times and we report some kind of average or something like that. But you did show some very interesting stuff. So first of all, there was, I think, a change on the no-op data set where you actually H-shot it, which means the model should be able to kind of filter away the distractors, but it didn't, which was very, very curious. But more broadly, though, isn't it interesting that you sample from these models a whole bunch of times and you see this huge variation? And what's the implication? Is the implication that when we use language models for doing reasoning, we should actually be kind of like sampling 100 times and taking the average result or something? I mean, because many of us use language models and we just sample once. We just assume that, oh, it's doing reasoning, that's the right answer. I mean, we don't really think about, well, if I asked it another 100 times, it would give me a bunch of different answers.
Yeah, I mean, about sampling, there are a couple of things. Like sometimes sampling in general doesn't make sense. So again, back to our example, 2 plus 2 equals, there's no sampling. It should be 4, right? Like if you increase the temperature, it could become 5, but why do you want to do that? Like randomly picking a number doesn't make sense at all in that sense. That's why for our study, we always stick to greedy decoding, no sampling, because like if you are doing arithmetics or you're doing reasoning, it has to be greedy. But in general, the other argument against sampling and majority voting and all those kind of things is the example I remember you had an episode where there was an example like if you let 10,000 drunken people go to after the bar go to home, eventually some of them may reach the home, but that doesn't mean they are able to like understand what's going on. Like given enough samples, you will eventually reach to destination probably, but that doesn't mean that's the issue. So actually there was a work that argued exactly the same thing. Like they said, like if you measure the GSM 8K and math accuracy and you sample the model 100 times, it will be like 20% better. But for the same argument, I don't think that's what we should study. Right?
Cool. Well, Iman, it's been an absolute honor to have you on MLSD. Thank you so much for joining us.
Thank you. It was great talking to you.